Good morning, my little chemistry Padawans. A little bit of pop culture Star Wars reference there. You are my little Padawans. How are we all doing? And I need to get rid of my echo. There we go. Echo's gone. How are we all doing? It's our third day consecutively of live classes, and hopefully you've been finding all the biology, chemistry, and maths ones really, really useful so far. Oh, and they start away. Thank you very much, guys. I thought I dropped that in yesterday, So thank you very much for the happy birthday wishes, guys. Really, really appreciate it. So of course, revision doesn't stop just because it's your birthday. Anybody that's got a birthday from this point until the middle of June knows that, the exams and revision and everything just kind of takes over, doesn't it? So thank you very much, guys. Really appreciate it. Best bit about having a birthday this time of year is there's loads of chocolate around as well, which is great. I'm not religious in any way. I don't follow any kind of denomination, but, Easter equals chocolate, right? So happy days. So no, that's nitrobenzene. That's Nigel the nitrobenzene at the back. If I can just change the focus on this camera, maybe you can see that in the background. There he is, and there's Mr. Potato Head there holding some ethanol too. There we go. So anyway, back to me. Are you back focused again? Probably not. There we go. So yeah, hopefully you guys have been finding these really, really useful so far. Okay. We're trying to kind of help you revise. Oh yes, just Potato Head. I do apologize. Yes. So in the chat, in the Zoom, people are saying, yeah, it's not Mr. Potato Head anymore or Mrs. Potato Head. It's just Potato Head. Yeah, go figure. But anyway, that is a Mr. Potato Head because they've got a mustache, I suppose. That's probably the best way to kind of denominate it, but there we go. Yeah, Mr. Potato Head getting drunk on ethanol 11 a.m. So even I'm not starting that early and it's my birthday, but there we go. Question, hello in YouTube. Welcome back if this is your kind of second or third session. Question from Amritpal. I went to University of Bath. Yeah, I studied pharmacology at the University of Bath. Cannot recommend it highly enough. It's a beautiful, beautiful city. Lots and lots of culture, lots and lots of history. University is like a campus university, which I loved. And I'm one of the most kind of respected pharmacy and pharmacology departments in the country. So I was very lucky to go there. Back in 1999, September 99 is when I started. So not even in this millennium. So what are we doing today? Well, we're going to look at some organic mechanisms. Now, today's class isn't going to be very, very long, okay? I'm not saying that just because it's my birthday. I want to get off and join Mr. Potato Head on getting on the drink. But I'm not going to sit here and teach you every mechanism, right? The content guide is there to do that. The mechanisms that you need to know are in the content guide. What I'm here to do is show you an effective way of learning not only the mechanisms in organic chemistry, but the links between all the molecules as well. How you turn a nitrile into an amine, how you turn an alcohol into an alkene, and so on and so forth. So obviously those of you in the TT course will have already discovered these organic cheat sheets that I have. But I just wanted to show everybody, because there might be some new people in here who haven't found those yet, who haven't seen those yet, and who don't know how to use them. So we're going to be doing a bit of that, but I'm also going to be talking about mechanisms and what the most effective way of learning them is. So I'll tell you what, first and foremost, let's talk organic cheat sheets, okay? So I'm just going to bring up on my iPad where you can find those. Now, those of you in YouTube, there's no link to those in the description, okay? I'm going to encourage you, and I think it'd be wrong of me not to kind of join the free trial, okay? If you're not already in there, or become a TT member, and I'll show you where these are, okay? So I'm going to share the old iPad here. And as usual, we need to unplug it back in. There we go. So in here, we have the content guide. This is the OCR content guide. It just happens to be on the ozone page here. So down the left-hand side, you'll see all the major parts. If you are thinking of joining the free trial, guys, and joining these lives within the Zoom, so you can join the chat during the live class, all you need to do is study support live classes and click on chemistry live class and recordings, and you will be taken to the page where you'll see all the links to the live class. You see the join live class button there. and you'll end up in the Zoom. The PDF, of course, links you to the PDF that we're using today, okay? So that's where you'll find the live classes. Now, the organic cheat sheets, there are AS ones, okay, which can be found in AS Organic Synthesis there. So that is an AS version of the cheat sheets, okay? You'll see those there. Oops, I didn't mean to do that. But anyway, I'll show you the AS version. So what these are PDFs that you can download and print out, okay? So this is the AS version. There is a full version where you've got all your tests, all your conversions, all your reagents. The little M in the circle denotes a mechanism that you need to know, okay? So the mechanism isn't on this page, but the reagents and conditions and the name of the mechanism are. Now, that looks nice, doesn't it? Year 2 people, year 13 people. The organic synthesis for year 2 is down here. Now, these come in 2 forms. There's an aliphatic one, like the one we've just seen, and we see it here. Look how busy that is. And there's an aromatic version. So here's the full version, M denotes mechanism you need to know, and here's a blank version. Okay, now this is really important, all right? Because the way to learn this is spaced repetition, okay? And actually doing or writing out the reagents, the conditions, the tests, and so on and so forth, okay? So active learning and spaced repetition are the key phrases here, okay, guys? So when you want to learn this, you print out maybe 10 or a dozen of these blank sheets, okay? And you see what you can complete in terms of the tests for the molecules, the reagents, the conditions, the names of the mechanisms, all right? Then you compare to the full version, make a note, mental note, obviously what you, or maybe even write on in red or something like that, the bits that you missed out, study it for a bit, try again, and then maybe leave it a couple of days and do it again. But every time you fill out this blank one, don't just add to it, you get rid of it, you throw it in the bin and you start again, because looking at something, you can stare at it for days on end and it's not really going to do any kind of, it's not going to do you any favors, okay? So I just noticed in the YouTube, I have got the chat there, but I'm not really paying attention to it. If you want to get involved and ask questions, guys, you need to be in the Zoom. And to do that, you can join the free trial. So there is your aromatic version as well. Okay, nice one. This one, because all the M's are the same. They're all electrophilic substitution. Done. Okay, but again, you get a blank version there. So of course, these are bespoke to your exam guide. So what OCR need to know, AQA might not, and vice versa, and EdXL is going to be different. So these are bespoke to the exam board that you're sitting. Okay. So if you want those people in YouTube, you're going to need to join the free trial, and you're going to need to go down to Organic Synthesis and you can download them from there. But I'm under no illusions. They're probably out there in the world anyway, to be honest with you, maybe on TSR or something like that. But ideally, come to the free trial, use the course, and you can use everything more effectively. Everything you need to know is in here, okay? Now, so that's all the different conversions. So spaced repetition, write it out, check it. Anything you get wrong or missed out, make a mental note, put it in the bin, start again, okay? And that will absolutely help you remember all these different conversions and things, focusing on those different changes between the functional groups. Now, I don't want to scare you, ladies and gentlemen, but there are a number of mechanisms you need to know. Okay, and they are difficult to remember, but some of you need to know more mechanisms than others. Now, what I'm about to show you, okay, is a summary of all these little M's, okay, in circles, all the different mechanisms that you need to know. So by exam board, showing you what you need, okay? Mez, drawing curly arrows everywhere and hoping for the best. This is what we want to avoid, isn't it, Mez? Okay, so we're going to go through some of the basic principles of mechanisms. Then I'm going to show you the most efficient way of learning these mechanisms. No, I'm going to not use that word learn. I'm going to use the word understand, because there is a difference. I'm going to get to that in a second, okay? So let's kind of get out of this and go to my old PDF viewer here, okay? So here we see AQA, OCR, and EdXL, 3 major exam boards. I'm looking at OCR A here, okay, not OCR B. So these are the different mechanisms you need to know. And you can see just by looking at this table, this is my summary that I wrote last night, that AQA, Gabriella, my teacher tells us and just screams, draw curly arrows in a strong Spanish accent. Well, you know, I'm not entirely sure just cracking the whip like that's going to help you learn it, but fair dues to them. So AQA do have the raw end of the stick here. There are every mechanism on there AQA needs to do. You can see where the blank spaces are for OCR and Excel. You guys don't need to know those. So you've not really got it. You're not as up against it as AQA. It's just one of those things in the AQA spec, okay? So essentially, this is what you need to know, all right? So don't be afraid, take a screenshot of this. I've not uploaded it because everything you need to know is in the organic mechanism cheat sheet, okay? So this is just to give you an idea of what you're up against based on what exam board you're doing. Most of these are aliphatic. Only the bottom one is the electrophilic substitution. If I could spell electrophilic, I need to change that. Essentially, philic. The ones at the bottom. So for example, there is a difference here. So with electrophilic substitution, you all need to know it, but in AQA, you need to know nitration, acylation, and alkylation. Okay, so adding an NO2, adding like a ketone group essentially, and adding a methyl or ethyl group, an alkyl chain. Same for everybody else. Okay, exactly the same actually for Excel, but OCR, you need to know halogenation as well. In fact, I think AQA needs to know halogenation too. So I'm going to put that on there. Okay, so there are differences, but of course, when you're in the content guide, you don't need to worry about this because everything that's in there you need to know. There's nothing that's in there that you don't. Okay. Zach saying, to be fair, with mechanisms, if you do quit, you can save time for other questions. Absolutely. So if you know these, it's easy money. Okay. Just like I was saying with titration questions yesterday, by using some of the tips and tricks I showed you, you should look forward to finding a titration question in your paper because you think, I'm all over this. Okay. And it's the same with mechanisms. So let's get to it, folks. All right. Let's look at some of the basic stuff. Now, there is a PDF. We will get to the PDF. Those of you in YouTube, you can find a PDF in the description. Those of you in the Zoom, in the TT members course, then you can find that PDF underneath the button where you joined the live class, okay? So let's start with the basics, okay? Because I'm just gonna go to the blank page here. In fact, where am I? Let's go to a blank page here and I'm gonna stop sharing for a second because I want you to listen in, all right? I want you to think about the difference between memorizing something and understanding something, okay? Really, really important. When you memorize something, okay, so you look at a mechanism and you just memorize it off pat, that's fine. And if you get that mechanism, so let's say it's the electrophilic addition of HBr and ethene, okay? And that's the simplest kind of alkene hydrogen halide that you're going to get. All right. And that tends to be the one what you learn. And you can just memorize that. Okay. Oh, well, that curly arrow goes there and that curly arrow goes there. And that's a dipole and that's a positive charge and so on and so forth. You could learn it off pat. The problem is with memorizing things like that is you can forget them. Right. So just by learning where the arrows go from and to, you stand the chance of forgetting it in an exam situation, you know, stress hormones high, you know, you can't access parts of your brain that you really want to access sometimes. And the other thing is, if you are faced with a molecule that's not ethene, okay, maybe it's 2-methyl-butanene or something like that, then you're not very well equipped. In fact, you're not equipped at all to be able to deal with that because you've memorized, you've learned HBr and ethene. Well, what if you've got HI and 2-methyl-butanene, okay? So there's two ways, okay, of getting across this. Number one is understanding how the mechanisms work and why they work. Understanding helps you apply your knowledge to any scenario or situation that you come across rather than just the one you learned, okay? Because of course, we all know in an exam, they're not going to give you ethene. They're going to give you another alkene that looks a bit more complicated. They're not going to give you a straightforward molecule. They're not going to give you methane for free radical substitution, for example, all right? So they're going to give you different things. And if you understand it, you can apply what you understand to those mystery compounds that you get in your questions. So learning these, memorizing these doesn't work. for longevity and to make sure you get the marks in some of the more difficult questions or mechanisms, then you need to understand it. Okay, and you need to understand why that curly arrow goes from here to here. You need to understand why is that a dipole and so on and so forth. And that will help you. So we need to not learn these mechanisms, but we need to understand these mechanisms. And the other thing, as I mentioned with the organic cheat sheet, is spaced repetition. Okay, so we're going to go through how we're going to do that today. A couple of comments in here. Where are we? Find this way of learning organic cheat sheet. I remember the ones I understand, but the ones I don't know much, they're harder to remember. Very well said, Alex. That typifies exactly what I've just said. So the ones you learn, you find it hard to remember, but the ones you understand, you find them easy to remember. It's a huge, huge thing, and nobody tells you this, okay? Megan agreeing with Alex in the chat there as well. So with that cheat sheet, you need to find it in the course, of course. But the PDF, which we're going to use very shortly, that's in the description of the YouTube, and it's underneath where you linked the where you've got the link to the live class. Okay, so we need to understand these mechanisms, not learn or memorize them. We need to understand them. Okay. Yasmina, I've been using the blank organic synthesis sheet for 15 days now, and after a bit, it does get less overwhelming. You just have to stick with it. Absolutely. It takes time, ladies and gentlemen. It does take time. You're not going to learn everything overnight. You'll just stress yourself out. So I know it's a very, the pressure's on this time of year for you guys now, but essentially, it does take time. Okay. Just spend, if you can, maybe like 30 minutes a day on it. All right. If you're really concerned about learning these organic mechanisms, 30 minutes a day, that will absolutely do you. Okay. So let's get to the basics. Okay. Let's start with our understanding of these mechanisms. Okay. So I am going back to first principles here. So I'm not going to make any apologies for that because everyone's at different stages. I think it's really, really important. So some key phrases and key terms or key things that we need to be able to do. Number one, spotting dipoles, okay? Because what you need to understand is that mechanisms are all based on electrostatic attractions, all right? So where you have a CX, so a C bonded to a halogen, you're going to get a dipole, okay? Where you have a C bonded to a single bond O, you're going to get a dipole. Where you get a C double bond O, you've got a dipole. NH, you've got a dipole, okay? Oops, that's not a positive. That's a negative. Okay, so what you need to look for in any molecule that you're looking to do a mechanism for, the very first thing you need to do is spot your dipole. Okay, the other thing, and I think it's not a dipole, is areas of high negativity. Okay, or high electron density. Okay, because they figure in a couple of mechanisms as well. So when I say an area of high negativity or high electron density, where am I looking at? Okay, Sarah, thank you very much in the chat. We're looking at a C double bond C. So an alkene, that's an area of high electron density. So positive things can be attracted to that. Absolutely. Where else? Matilda, benzene ring. Absolutely. So our pi system in our benzene ring, okay, that's another area of high electron density, and positive things will be attracted to that. Okay. So if I was to draw out this molecule like so, okay, if I had a nucleophile. Now, a nucleophile is, of course, something that's attracted to something positive. Okay, it's electron rich. It's either got a negative charge or a delta negative charge. Where is that actually going to be attracted to on this molecule? The carbon bonded to the Cl, absolutely. So if you've got a nucleophile, spotting your dipole, delta positive, delta negative, your nucleophile is going to be attracted to that C delta positive there. Okay, so again, it's about spotting dipole. But then if I had something like an NO2 plus, so an electrophile is something that's positive. I've got a delta positive on it. It's electron deficient most of the time. That's going to be attracted to our electron ring. But of course, the arrow goes the other way. Good. Okay, because what does a curly arrow denote? What are we showing with a curly arrow? Good. Movement of, very specifically, so curly arrow equals the movement of a pair of electrons, okay? Now, if you ever read anything about half-headed curly arrows, okay, you do not need to use them. In none of the specs, none of the major specs, AQA, OCR, EdXL, do they require you to use half-headed curly arrows, because that's for the movement of one electron, okay? We're always concerned with a double-headed arrow, which is the movement of a pair of electrons, okay? Free radicals, Imran, they would be involved. If you to draw the mechanism for free radical substitution, yes, you would draw half-headed curly arrows, but actually you will never be required to do that, okay? It's just a set of equations, isn't it, for free radical substitution? So you will not, under any circumstances, in an A-level paper for the current specification, need to use half-headed curly arrows, okay? So you're always going, before you draw a curly arrow, just say to yourself, right, where are my electrons? Where are they going from and where are they going to? Curly arrows always go from where there's lots of electrons to where there's less electrons, okay? Because they move from where there's lots of them to where there's not so much of them, okay? So for example, I think somebody mentioned it in the Zoom chat, that a curly arrow will always go from where, okay? Where will your curly arrows always go from? Give me some examples of where curly arrows can go from. Good. So curly arrows can go from a lone pair. Okay. So if, for example, if you had something like NH3 with a lone pair in it, the curly arrows would be going from that. A bond. Okay. So a single bond. So like in electrophilic addition, okay, you get your curly arrow from this bonding pair here. You don't need to draw the electrons in, but they will go to the Br, or a benzene ring. Good. Okay. Oh, in fact, we should write double bond there as well. Okay. So a lone pair, single bond, double bond, or your benzene ring. Okay. So that's where the only places where you're going to get electrons moving from. Okay. And of course, where they're moving to depends on where you're making the new bond. Okay. So they always go from a lone pair, a covalent bond, let's just say that, or the benzene ring, and they always go to the thing that is now bonding to it, okay? Specifically the atom that's bonding to it, okay? That's benzene down the bottom there. It's meant to be it's meant to be benzene, but I run out of room, okay? So you need to be really clear on the definitions of these different things, okay? So let me just show you back in the course really, really quickly. So if you want to spend a bit more time, and I recommend you do if you haven't done so already, looking at the fundamentals of mechanisms, go into basic concepts of organic chemistry. This is in the OCR course, but it's the same in the EdXL and AQA. Introduction to organic mechanisms. Okay, that's a 12-minute video. But what this does, it comes with a cheat sheet, obviously, and I go through everything that I've just been talking about here, all right? And also organic reaction key terms. This organic reaction key terms video will go through all the different terms that you need to know and be clear on in terms of organic reactions. And we start with nucleophiles and electrophiles, addition, substitution, elimination. So understanding what the name means is really important as well. So let's have a look at the different types. So we've got nucleophilic, okay? We've got electrophilic. All right. Now, these are our, if you like, attacking species, okay, to our organic molecule. So these equal the attacking species attacking species. So they're not referring, can't spell, come on, Rich, not referring to organic molecule. So your other reagent, okay? So an electrophilic, sorry, nucleophilic could be something like an OH minus. Electrophilic could be something like NO2 plus. So it's whatever the other reagent is. And of course, the other half of the mechanism name, addition. So for example, electrophilic addition. So What are we doing? Well, we're adding atoms to the molecule. Okay, we can get electrophilic addition and nucleophilic addition. When it comes to electrophilic addition, what's the only organic molecule that undergoes electrophilic addition? Alkenes, okay? Alkenes. So if an alkene is being reacted with anything, it's only an electrophile that's going to react with it, okay? So if it's an alkene, it's electrophilic something, okay? Electrophilic addition, it'll be electrophilic addition, bottom line, okay? So in terms of nucleophilic addition, this one is a year 2 only. This is your carbonyl to hydroxynitrile. And we're going to look at that one in a bit specifically, okay? So we are adding atoms into the molecule. You know, these carbonyls don't have C double bond C, but what they do have is a C double bond O. So again, it's that double bond that's the commonality between these two things, okay? Alkenes have got a C double bond C, they can undergo addition. Carbonyls have got a C double bond O. They can undergo addition, but it's a different type. It's nucleophilic. Why? Question, and I'll just draw an aldehyde here. Why is it nucleophilic addition for aldehydes and ketones and not electrophilic addition? Good, Matilda, brilliant. Mez as well. So we've got a dipole there. And the thing that our nucleophile is attacking is this carbon here. Okay, so right back at the start, I said, spot your dipoles. That's exactly what we've done here, okay? So electrophilic addition, alkenes. Nucleophilic addition is going to be a carbonyl group with your hydroxynitrile. That's the CN minus, okay, that gets added here. So that's addition. They're the only two places you'll find it. Substitution. Instead of adding molecules where we have room, don't we? If it's unsaturated with a double bond, we can add things in. Saturated molecules tend to undergo substitution, so you swap. Okay, e.g., let's say a bromine for an OH or a chlorine for an NH2 or something like that. We're literally taking one group out and adding another group in. Okay, so substitution happens there. It also happens with benzene. You're absolutely right there, Raina. In benzene, what we're doing is we're taking one of the hydrogens that we don't normally draw on benzene, and we can swap it for something else. So that might be a methyl group or an acyl group, so you end up with a ketone, or it could be a halogen or something like that, okay? So substitution, we're swapping one thing for another. And then lastly, I mean, we do have addition elimination. I'm not going to get into that year 2s, okay? There is an addition elimination where kind of two things are happening, but that's only one example. You need to know that. Elimination. What do we always make in an elimination reaction? An alkene. Some people saying water. That's when you go from an alcohol to an alkene, you get water. But if you went from a haloalkane to an alkene, you wouldn't get water, would you? Okay. So what you always make in terms of organic, always make an alkene. Okay. Now, the reason is if you've got a saturated molecule and you take a group away from it or an atom away from it, it has to form a double bond to compensate. Because, of course, all our carbons always need, apart from in benzene, 4 bonds around it. Okay. So when you take atoms away, double bonds have to form. So if it's elimination of any kind, okay, or if you're forming an alkene, then it has to have been an elimination reaction. Okay. If you've got an elimination reaction, you have to be forming an alkene. There's no two ways about that. Okay. So in terms of elimination, it's just elimination. Good question in the chat. Can it be electrophilic or nucleophilic? We don't say electrophilic or nucleophilic for this. It's just elimination. So just to kind of go back to, if I can, have I got my organic summary cheat sheet here? So you can see over here, our elimination going from haloalkane to alkene, dehydration and elimination from an alcohol to an alkene. You will not find the word elimination anywhere else on this sheet, apart from this nucleophilic addition elimination over here. But you know what? That's you can check that out in the content guide. I don't want to muddy the waters with that here. Okay, it's a bit of a weird one, that one. So obviously oxidation and reduction we should know and love as well. That's obviously between alcohols, aldehydes, ketones, and carboxylic acids. That's what we're looking at there. But the main ones are these things here, okay? Just know and understand what these words mean. It's not just a name. Like everything else in organic chemistry, it's descriptive, okay? It tells you exactly what's happening. Nucleophilic addition. Right, well, you've got a nucleophile. Something's going to be negatively charged, okay, if it's a nucleophile, and it's going to be attacking something that's delta positive or positive. That's nucleophilic. Addition, well, I'm going to be adding something into the molecule, okay? So just always look at the name, all right? And of course, if you need to get the name from the mechanism, then just look at what's happening in the mechanism, all right? Am I taking something away? Am I swapping something, or am I adding something? Okay, am I eliminating, am I substituting, or am I adding? What's my reagent? Okay, what is attacking my organic molecule? Is it a nucleophile or an electrophile? So you can work these things out. You don't need to memorize it. Again, coming back to you know, learning and understanding something as opposed to just memorizing it or learning it. Okay. Matilda making a very good point here, okay? They repeat. A lot of the mechanisms repeat. And so it looks really, really overwhelming, but some of them are the same mechanism with slightly different reagents. Absolutely. This is typified by, where are we? This one here. There are 5 mechanisms to learn on this cheat sheet here. Or are there? No, there's one mechanism to learn. Every single one of them is electrophilic substitution. So you can take that and just, it just makes you feel a little bit better, okay? Like in this one here again, over here, we have got nucleophilic substitution, nucleophilic substitution, nucleophilic substitution, okay? Nucleophilic substitution. They're all the same mechanism, all right? They go through the same kind of motions in terms of moving electrons and curly arrows and dipoles and things like that, but you're just using slightly different reagents, okay? Megan, good advice. Megan color-coded the mechanisms on this sheet to dissociate, you know, what's the same as the others. So maybe you could do all your nucleophilic substitution reactions in green like that, and then all your addition elimination reactions, all your electrophilic addition reactions, you could probably do in purple, okay? So you could just whittle them down in terms of the type of mechanism you're looking at. And if you understand it, then you can just change that mechanism ever so slightly, okay? And that will make you feel better. It will make it seem less overwhelming, and you know, the stress levels go down, and you know, you can learn them a lot more effectively and understand them a lot more effectively. Excuse me, lots and lots of talking. Right. Shall we actually put pen to paper? I think that's a good idea. So as long as we're all on board, right, and I want you to remember this, excuse me, I do apologize. Another bit of advice is drawing out the full displayed formula. Okay, drawing out the full displayed formula is really, really important, because then you get to see your dipoles and stuff like that. So let's put pen to paper. Okay, yeah, little cheeky burp there. Okay, so this is your PDF that I have kind of given you guys today, and we're not going to go through every mechanism, all right? Because I could sit here and just draw out one mechanism or one example of each one, and that wouldn't do you any good. Okay, what I'm here to do today is show you the technique of understanding mechanisms and applying them to unknown scenarios and things like that. Okay, so this is the idea. Now I've given you this sheet to kind of give you a head start, and you can create your own after this, and I'll tell you how to actually use them. Okay, so what we've got here is free radical substitution. All right, I'm going to just talk you through the first part here. Excuse me. So free radical substitution, write the initiation, propagation, and termination equations for the chlorine free radical substitution of the following. So we're starting with ethane, okay? So in terms of our initiation, that's always the same, okay? Initiation, we take Cl2. What's our one condition we need in order to make 2 chlorine-free radicals here, guys? Oh, you're already all over it in the chat. UV light, absolutely. UV breaks that bond. Homolytic fission is the only place, a little bit of ozone maybe as well, if you need to do that. But this is the only place you're going to find homolytic fission where one electron from of the pair goes one way and one goes the other. Okay, that's homolytic fission. And if you were to draw it, okay, you got that Cl-Cl bond here. You could use, this is where half-headed curly arrows would come in, but they wouldn't expect you to know this. But this just shows you one electron goes one way, one electron goes the other. You end up with a chlorine-free radical. And just to kind of hit things home, a chlorine atom has got 7 electrons in the outer energy level. This single one, this unpaired electron here, that is your free radical. Okay, that's what makes them so reactive. It's just a chlorine atom. That's all it is, okay? It's nothing magical. It's just a chlorine atom with an unpaired electron that's just looking for love. It needs something, anything, in order to create that full outer energy level and bond with, okay? So that's why they're so reactive. Now, propagation steps. I want to show you a couple of little tricks with this, okay? So propagation. Your chlorine-free radical with ethane reacts with ethane, so C2, H6, and what we make is I'll tell you what, let's not use the molecular formula. Okay, so CH3 we can actually go to dot CH2 CH3. I always try to put the dot on the atom where the new free radical is. Okay, if they say molecular formula, that's fine. Okay. Rich, I have a question about the if they say molecular, do you have to put all carbons together? Yes, if they ask for the molecular formula, you should really group all the same elements together. That's what they should do, but they wouldn't do it in this because they need you to talk about structure and stuff as well. So we get HCl, okay, which is our byproduct. The second step in propagation is our new free radical, CH2, CH3, plus full-on chlorine, and that gives you CH2Cl, CH3, and a regenerated chlorine-free radical, okay? So these 2 propagation steps for ethane, nice and simple, really, okay? But what I want to show you is this. First of all, if, let's say, I'll use purple, why not? If you remove anything with a free radical on here and merge the 2 together, what do you end up with? Good, Sam. Sana as well. Mez, the full equation for the reaction, the overall equation for the reaction. So that is your acid test. If you're just wondering, if you're not sure whether you got your propagation steps correct, just on a separate bit of paper, just cross out anything with the with a free radical on it, with that unpaired electron, and merge the 2 together. So we'd end up with ethane plus chlorine gives chloroethane and HCl. Okay, so you can see merging those 2 together actually gives you the full overall equation. So I'm just going to leave that one with you. How many steps are always part of the termination? 3. Good, absolutely. So this is just different combinations of free radicals you have in your propagation steps. So you could have Cl bump into a Cl free radical and make Cl2. You could have a Cl with our CH2 CH3 free radical, and that would give you CH2Cl CH3, which is actually an overall product, which is great. And then lastly, you could have 2 of these organic free radicals, and what you'd end up with is I'm just going to do the molecular formula, C4H10. So you could, this is a common question actually, how do you end up with a molecule twice the size of the one that you put in there? It's because of this particular termination step. Okay. In the initiation step, instead of Cl radical and Cl radical, put 2Cl radical. Is that okay? Yeah, absolutely. You can just put 2Cl dot there. That's absolutely fine. So all the steps follow this pattern. 1 equation for step 1, 2 equations for step 2, 3 equations for step 3. And that is a very good way to remember it around here. And that's what I say in the content guide video as well. First step, one equation. Second step, propagation, 2 equations. Termination, third step, 3 equations. Okay. You always write UV in that first one there. Yeah, absolutely. So this is what I'm talking about. I'm talking about, all right, you probably learned it with ethane or methane. That's absolutely fine. But what you guys need to do is to be able to write these 4 molecules that they are likely to give you in an exam. So they're not going to give you a nice, straightforward, like alkane to do this with, okay? So what I'd like you guys to have a go at is this. We've got 2-chloropropane. Now, my question to you is, what happens to that chlorine on 2-chloropropane if it underwent free radical substitution with chlorine free radicals? What would happen to this chlorine here during the reaction? Megan's saying it'd be removed. Any other takers? Makes Cl2, stays there, nothing. The answer, ladies and gentlemen, is absolutely nothing, okay? Because in free radical substitution, every single time you are taking out, you're swapping out a hydrogen. Remember, it's substitution. You're swapping a hydrogen for a chlorine or whatever it might be. It's usually chlorine, okay? So what you can do is if you get a molecule like this, then this bad boy stays exactly where it is. It doesn't get moved at all. Feel free to substitute any one of these hydrogens, okay? But that chlorine stays there. That does not get substituted for another chlorine, because what would be the point, right? So if you get a molecule that's already got chlorine on, that you leave that there and it stays part of the molecule. So if we were substituting one hydrogen, we would end up with dichloropropane, okay? It could be 2,2-dichloropropane, or it could be 1,2-dichloropropane, depending on which of these hydrogens you substitute. What I will say is, and my final thing on this is, if they ask you, okay, if this question said, in fact, you know what? I'm just going to get you to do it. I'm just going to get you to do it. All right, I'm going to shut up. I want you to write the propagation and termination steps. No point writing initiation. It's the same, isn't it? But I want 2-chloropropane converted to 1,2-dichloropropane. Specifically, I want you to draw or write the equations for the production of 1,2-dichloropropane. Use the displayed formulae. Okay, use a displayed formulae to do this. I'm going to give you 4 minutes. Okay, I'm going to set the old timer. So, four minutes, go. So I want you to write the propagation and termination steps using displayed formulae for conversion of 2-chloropropane to 1,2-dichloropropane. All right, specifically making 1,2-dichloropropane. So I want you to write out the propagation and termination steps for this. Okay, propagation and termination. Rania, how would you know this is a propagation question? Well, this is just the sheet. I'll tell you how you can use these sheets later, okay? I'm just using these as examples. I'm telling you what the question is here, okay? So, just listen to what I'm asking you to do as opposed to, in a question, all of them, all the termination steps. So I want both propagation steps and I want all 3 termination steps, please, guys. And in fact, while you do that, I'm going to do it as well. Okay, guys, you've got 30 seconds left. 30 seconds left. As I see your question. I see both your questions and I'll answer them in a sec. Mariah has started singing. Matilda, this live class is probably going to finish in the next kind of 15 minutes or so, okay? It's not going to be very long at all because I'm just showing you the methods and I want you to be clear on the methods, okay, to learn these. All right, okay, so boom. So what we've got here looks a bit messy. I do apologize for that. So the propagation step here, we've got our 2-chloropropane reacting with a chlorine free radical. Now, it doesn't matter whether you chose the hydrogen I did here or this one or this one or this one or this one or this one, whichever one you chose, it's absolutely fine because you're going to make 1,2-dichloropropane. Okay, it doesn't matter which of those hydrogens. The only one it can't be is this one, because that wouldn't get you 1,2-dichloropropane. It would get you 2,2-dichloropropane. Okay, so seeing how I'm being specific here. So then that moves on, and again, you can see where that free radical was. That's where my new chlorine is in the second propagation stage. Okay. Now, termination wise, obviously we've got your classic 2 chlorine free radicals. This one here producing your overall product, okay? So your 1,2-dichloromethane, the 2 different free radicals. But here, and I can see Amritpal in the YouTube, just glanced over there, you get 2,5-dichlorohexane as a consequence of these two, because imagine these two bonding together. So you end up with a 6-long carbon chain, okay? And then you end up with the 2,5-dichlorohexane there. So what I'm going to do is I'm going to get rid of all of these. And I'm just going to show you one last thing here before we move on. Okay. With this molecule here, and I said to you, this molecule, which is ethyl benzene, okay, ethyl benzene, this is mixed with chlorine in UV light. Now, where will the chlorine bond? So if I mix this compound with chlorine in the presence of UV light, Jawadul, end of the chain, Alex saying just the chain. Absolutely, you are 100% right. So obviously this is skeletal. I'm just going to draw on my hydrogens here. You got 2 there and you've got 3 here. This is just an ethyl group. So it's basically this, okay, CH3 and CH2. It's just an ethyl chain. Any one of those hydrogens, 1, 2, 3, 4, 5, could be substituted by your chlorine, okay? Any one of those, but not any of these, okay? There's 1 hydrogen in each of those in benzene. They do not get touched, okay? Because those hydrogens is much more difficult to substitute those. You know, you need an electrophile, okay? You need a really strong electrophile in order to undergo substitution there, okay? Yes, it's more stable, higher bond enthalpy, all of those things. So if you ever get a question like about free radical substitution, there's a cheeky little benzene ring present, then you don't touch it. It's only going to affect the alkyl groups bonded to the benzene ring, okay? And of course, they would always be there. So what I'm saying with this is, okay, and it's not just free radical substitution, we can do this for. The best way to learn these, okay, is to start with a simple molecule like ethane, okay? Start with a simple molecule like ethane and draw your mechanism out for it. Then give yourself a slightly different one. 2-chloropropane, for example. Then give yourself another slightly different one, which like ethyl benzene or something like that. So what you're doing is you're not just learning off pat one mechanism for really simple methane or ethane, okay? What you're doing is giving yourself more likely molecules that you're going to come across in an exam. There's no rules to this, all right? So long as it's an alkane of some description, you can write out the equations for free radical substitution, okay? So this is just a starter for you guys. If you wanted to draw, give yourself some other weird molecules, maybe something that's got an alkene group in it, which doesn't get affected. It's only the alkyl group that you're focused on, okay? So again, spaced repetition. So draw the mechanisms out for these, okay? Double check them. If you get any of them wrong, just scrap it and do it again. Now, what I would do is do this for each of the mechanisms that you need to know. Each of the mechanisms that you need to know. So here's another one for you. Nucleophilic substitution, okay? Now, I haven't given you a nice simple one to do like chloroethane, okay? And substituting with OH minus. What I've done is I've given you some different ones to do in terms of practicing these mechanisms, all right? And again, you can make them up yourself, all right? But the way to do this is just, it's about applying your knowledge of where the curly arrows are going from and to, okay? Spotting those dipoles, making sure you put in your full charges where they need to be on the intermediates and so on and so forth, okay? So, draw the mechanism for the nucleophilic substitution reaction of 2-methyl, 3-bromobutane. So butane, 2-methyl, 3-bromo with OH minus, okay? Is it clear to you once you've drawn this out where that OH minus is going to attack? Yeah, where's it going to attack? Good. This delta positive of this dipole here. So you're going to get this nucleophilic, nucleophilic attack here, and then the reaction continues. What about 1, 2, 3, 4, 5, 1-chloropentene? So that's 1-chloropentene. Where's that going to attack? Well, of course, it's going to be here, okay? So that's where your CN minus is going to attack there. And then last one, cyclohexanol. Now, this is what throws a lot of students as well. So this is not benzene, it's cyclohexanol. So cyclohexane with an OH group on it, okay? So here you're going to get your delta positive on this carbon and your delta negative on the oxygen, okay? And your Br minus is going to attack that carbon there, okay? So it doesn't matter where you put the minus on the OH. Not really. I would always put the lone pair on. That's the most important thing for me. It's going from the lone pair there. The lone pair on a cyanide ion is on the carbon, okay? And we just put the minus top right because that's just where it belongs, okay? And here, of course, you've got your bromine. Curly arrow should go from your lone pair here, okay? So it's just a case of taking yourself out of your comfort zone and doing these mechanisms for molecules that have other things going on, like there's a methyl group on this one, there's an alkene group on here. This is actually a cycloalkane. But the principles of the mechanism do not change, okay? And last but not least on this worksheet is one for the year 13s. This is the nucleophilic addition reaction. So starting with ethanol, nice and easy with CN minus. 3-methyl pentan 2-one, okay? So again, we're throwing something else into the mix in this molecule. And here we also have, this time, a benzene ring with a ketone group attached. And of course, this doesn't figure. You know that there's a dipole here and the CN minus is going to attack that carbon there, and you're going to end up with your hydroxynitrile, okay? So I'm not going to go through these. Like I said, some of you need to know, I think all of you need to know nucleophilic substitution. I'm going to stop sharing for a sec. All of you need to know nucleophilic substitution, electrophilic addition, electrophilic substitution, okay? But this is what I want you to do, and take note. Heed my words, ladies and gentlemen, okay? Treat it similarly to the way in which you're using your organic cheat sheet, okay? Set yourself up one piece of A4, okay, and write them out on pages or Word or whatever you're using, okay? Set them up and give yourself maybe 5 different like starting molecules. Okay, so if we're doing nucleophilic substitution, give yourself 5 different haloalkanes. Or if you're doing electrophilic addition, give yourself 5 different alkenes. Maybe throw a cheeky kind of like ring structure in there, or maybe some other functional groups. Make them up. Okay, and then what I do is apply your knowledge to those mechanisms. See if you can draw the mechanisms for each of those different scenarios. All the mechanisms are going to be the same because they're all electrophilic addition or nucleophilic substitution, and so on and so forth. And then obviously double check it, okay? I mean, you're not going to have the answers to this. There's no mark scheme, but you shouldn't need that. You'll know if you understand these mechanisms, you'll know if you got them right or not, because you know what your product should be for a kickoff, okay? So it's just to make sure that you understand these mechanisms, and you can work these mechanisms out for molecules that are not simple, that are not, like methane or chloropropane, or, like throw other things in the mix there. Okay, so you're applying your knowledge of the mechanisms to more kind of unfamiliar molecules. All right, but also spaced repetition. Okay, it's a case of just having a go of one day, and then leave it a week, and then have a go at it again, or leave it a couple of days and have a go at that worksheet again. Once you've done it once, don't keep it and put it in your notes. What's the point of that? Throw it in the bin, print off another blank one, and do it again. Okay, now that spaced repetition on active learning, okay, is going to be the most efficient way of learning these mechanisms. Understanding these mechanisms. Okay, now again, AQA, you are up against it. You've got more to learn than OCR and EdXL possibly put together. But like I said, I mean, speak to your teachers. Okay, speak to your teachers about what's going to be on your assessments. Ask them maybe to specify, as much as they can, what areas of organic chemistry that you need to revise. Okay, Shania, Rich, on Nuke Sub, how is the last one possible? Like BR, how's the last one possible? Like BR and nucleophile? Yeah, well, it is. I mean, how can I put this? OCR and EdXL need to know the nucleophilic substitution from alcohol to haloalkane. It's perfectly possible, okay? AQA don't need to know that reverse reaction. You only need to know from haloalkane to alcohol, okay? So that does work. That does work, all right? So the mechanism is the same. So just because it's not on your spec doesn't mean it doesn't happen. That makes sense, okay? Does that answer your question, Shania? Yeah, so AQA people, you don't need to know that. OCR people, I think you do need to know the mechanism, but EdXL people, you need to know the reagents, but you don't need to know the mechanism. But the mechanism's the same. Whichever way you're going, it's nucleophilic substitution. Nothing's going to change there, okay? Is it better to do topic or full papers? I mean, your teachers should be largely grouping your assessments into major areas. I don't think there's any harm in revising by topic, but it's hard to find questions, especially for OCR, that just focus on one topic. So just be aware of your common topic links, guys. In the content guide, okay, I'm still recording a few of them, but the majority are done of the videos where I'm actually just saying, like, these are the topic links. These are the things that can kind of contribute and join these topics together. So you're likely to get questions on them together, like Le Chatelier's and rates of reaction. Okay. They love sticking those two things together, and so on and so forth. Okay. Forrest, not going to do any exams in May. What should you do? Well, I mean, when are you going to do your exams? I think that's the most important question. Oh, you've done your exams. Wow, you're all done and dusted. Wow, Forrest. Keep abreast of it. Just keep on top of things, okay? That's all I would say. So when you're revising these, okay, and this is going to be my final takeaway today, guys. And like I said, I'm cutting this a little short, but you got this sheet to get you started, to give you an idea of what you can create, okay? I would 100% focus on active learning, drawing these mechanisms out for different molecules. If you see a molecule in an exam paper, think, that would probably undergo electrophilic addition. I wonder how the mechanism looks for that. And just do that. And again, spaced repetition, okay? Understanding why. Every time you draw a curly arrow, think to yourself, Don't just put it there because you think it goes there. Like, oh, I remember that it goes there. Say to yourself, why is it going from that place to that place? Why is that a dipole? Why is that fully charged? And so on and so forth. Okay. No, I can just see in the YouTube chat that somebody I know is wishing me happy birthday and telling me my time's up. Right, guys. Obviously, if you've got any questions, please leave me a comment in the course. Liam, on this day, a legend was born. Oh, bless you. Thank you very much. Imran, I think I will. Thank you very much. So hopefully that helps. And like I said, I wasn't here today to kind of go through every mechanism with you. The content guide does that. Everything you need to know, nothing you don't. I explain the mechanisms in there. But when you're learning them, when you're understanding them, spaced repetition, and of course, make sure you're applying it to different molecules. Don't give yourself a little safe space using nice tiny little molecules. Look at the exam questions for inspiration and see if you can draw them for different molecules and take yourself out of your comfort zone. Okay. So thank you so much for coming along, guys. I really, really appreciate it. We've had a great week this week and more to come next week with some more calculations and some other tips and tricks to help you learn the content quickly. Okay. But again, those of you in YouTube, don't forget, free trial. All right. If you are a member on the student room, I might suggest that you should go and look at your inbox because you might have an email from us. And yeah, I will see you next Tuesday. I will put the schedule up on YouTube and in the course very, very soon. But rest assured that chemistry is going to be 11 o'clock on Tuesday, Wednesday, Thursday next week as well. All right, guys. So thank you very much for coming along. Work hard. Don't forget to take breaks and relax. And that way you'll stay fresh and you can keep going. Okay. So good luck with everything. And I'll see you next week.